All right, welcome back, everyone. We'll be starting the next session now on interfaces, where the first talk will be given by Alexander Frolov, who will be joining us remotely from the DIS lab in Moscow, and he'll be telling us today about integrating Charm++ with a graph analysis DSL.
Okay, thank you very much. First of all, I would like to thank organizers of Charm++ workshop for allowing me to make a remote talk. I'm Alexander Frolov. I'm an engineer in Scientific and Research Center of Computer Technology in Moscow. And at the same time, I'm working on my PhD project that is relating to large-scale graph application and Charm++ and domain-specific languages. As we know that large-scale graph applications have become a hot topic in HPC community as well as in the data community. So that's probably because we all live in a world where there are a lot of large graphs, and here on the slide you can see the most common application where large graphs can be found. Such applications include web graph analysis, social network analysis, bioinformatics, human brains researchers. This application needs and forces the focus of the computer scientists to develop new programming tools which allows to run these applications on big parallel machines, and this is a really challenging task. So this task is correlated with some common challenges of parallel programming, such as we all know that design of efficient parallel algorithms is very challenging, and it always and it frequently depends and relies on the computer system architecture, such as interconnect topology or enabling GPU or CPUs. So that always takes a lot of human resources to develop efficient algorithms for every new application. But graph applications also introduce specific challenges, such as the necessity to deal with large amount of short messages which are generated in graph algorithms, and well-known techniques to use message aggregation to enable utilization of network bandwidth. And another problems which occur in graph application are related to graph distribution, static as well as dynamic. There are graphs that can be statically well distributed among computer nodes, but some graphs are skewed and they can be dynamically reconfigured and very irregular. Dynamic means to compute load to balance computation on the nodes are also very important, and that if this is done manually by application developers, it will take very much. It can take very much efforts, and it needed to be done in some abstract way to make easier life for application developers. Also, there is no parallel graph standard library. There is a famous library called Boost Parallel Graph Library, but If you're a data scientist and don't know how to program in C++ very well, you probably won't use it because it is a highly templated library and needs understanding of C++ concept. So other initiatives such as GraphBlast are still in a very early development stage, and it is cannot be used now by by data scientists. So here I showed some results of very rough assessment of relative programming efforts, which are mainly based on codes which I found in internet, in GitHub. So you can see that sequential implementation of graph algorithms is it's a starting point, and I relate different programming models to this, and using a shared memory model is very easy and did not take a lot of line of codes. But when we start to use MPI for implementing graph algorithm, the efforts to use it are relatively high. In the right two columns, you can see char++ and giraffe. Char++ implementations of graph algorithm. That was my experience. And giraffe is a open source Fraggle, Google Fraggle implementation. Is a specific graph framework, and you can see that it has relatively high productivity compared to, for example, to MPI. So nevertheless, these cases are very simple, and when the real application are developed, the things can change, and it can be very difficult to implement such applications. So researchers from around the world have focused their attention on domain-specific languages, and in Stanford University, one of such languages has been developed. It's called GreenMark. It was announced, and the first paper was published in 2012, and the first implementation of GreenMark was based on sequential C++ and OpenMP backends, and showed rather high effectiveness. Then, after 1 year, new backends have been developed, and they are based on Fraggle computation model, and exactly on GPS and giraffe libraries, which enabled to run GreenMark programs on distributed systems. GreenMark is open source, but open source version which is hosted on GitHub no longer supported, and GreenMark is now a part of another research and development project called PGXD, which is currently developed in Oracle Labs. So I made the comparative analysis of other different languages, and it showed me that GreenMark, first of all, it was only one which is open source, and it allowed very simple and expressive programming model to design graph algorithms, and I decided decided to try GreenMark to use as a front end for parallel programming system for graph applications. So here you can see an example tutorial program, which is computes average number of followers for some social network. Each followers has age from 10 to 12 to 20 years, and each user has age greater than k. So we should compute the average number of such followers for such users. You can see that procedure called average team count has 4 parameters. One is actually for graph, G for graph, age and team count have type n/p. That is from node properties with type integer, and k is an integer which specifies the age of the vertices. So for each loop, iterates over all vertices of the graph, and for each vertices computed number of neighbors with age from 10 years to 20 years. After that, a reduction is computed for vertices with the condition that age property is greater than k, and the returning value is average, stored in the average. So this is a very simple program, but it shows how GreenMark look like. And GreenMark actually is a data parallel language. It looks pretty much similar to OpenMP, so that is probably why the first backend for GreenMark was an OpenMP. In the site of PGXD project, you can find pretty many implementation of graph algorithms in GreenMark. So GreenMark is interesting that in that way as well. Why I thought that GreenMark implement GreenMark on Charm classes is not a bad idea. First of all, I haven't found GreenMark backend for HPC clusters. For distributed systems, as I said, there was such backends, but for HPC not. Also Char++ is a mature framework for parallel programming with active community. As we all know, that Char++ shows nice scalability on large number of nodes. Char++ computation model, from my point of view, is very fine and very suitable for expressing vertex-centric parallel graph algorithms. Char++ supports load balancing, which is essential for graph application, and GreenMark compiler has already had a Fraggle-like backends, Giraffe and GPS, which makes porting of Char++ porting it to Char++ much easier. I have been studying a usage of Char++ for graph application for significant time, and I found that there are two approaches to do it. The first one is vertex-centric. It is characterized by using a direct mapping of vertices on chairs. So we have the same number of chars in char++ program as the number of vertices in the graph. So it allows to write programs very easily. The program completion is detected by mechanism of license detection, and it's very suitable way to program graph application. Another approach is to use subgraphs in char++ chars and to manually distribute vertices to chars. It allows to obtain a coarser parallelism, but takes more time to develop application. It is important to say that the first one, vertex-centric approach, causes very extremely fine-grained parallelism, and as we know that it's challenging for runtime system, and there are works are going on to improve it for such laws. So what is the main challenge to translate GreenMark to char++? Actually, when I was preparing for this talk, I thought that it is almost the same as we would like to translate an OpenMP to char++, because GreenMark programming model is based on data level parallelism, while char++ is a asynchronous message-driven programming language. So this is a challenging, but this particular scientific task has been solved by GreenMark developers when they developed backends for Fraggle. Actually, Fraggle has a very close model to char++. It also works with objects, but it is a bulk synchronous parallel execution model, and so it's a significant difference. But for compiler, it's not so important, and very almost, I think, 80% or maybe 90% of efforts for translating GreenMark programs to char++ has been solved when the developers of GreenMark designed backends for Fraggle. And the solution was to build a finite state machine to control master-slave execution of the GreenMark programs. But not every GreenMark program can be translated to Fraggle, and there is a Fraggle canonical applications which has defined features which allows them to translate to such a finite state machine presentation. Okay, so I will move further. As I said, that char++ and Fraggle have much in common, but they also have principal differences. As I said, it is an asynchronous message-driven computation model in char++ and step-based bulk synchronous parallel in Fraggle. Also, in char++ we are able to set numerous entry methods when in Fraggle we have only single one, compute method. And in char++ we have automatic license detection mechanism, while in Fraggle we have semi-automatic, that is all vertices should vote to hold that is a special call must be done, and only when no active vertex in the program, then the computation will be stopped. GreenMark compiler is organized in a pretty standard way. It has a front-end and back-end. Front-end includes parsing and analysis step, as well as platform-dependent optimizations, while back-end has platform-dependent optimization and code generation. Actually, what I did, it is I integrated new code generation functions and step to the Fraggle backend, but also I made some hacks in the platform-dependent optimization as well to enable some lifting of the requirements for programs which can be translated to CHARM++. This is the example which I showed in the beginning, and in the right side of the slide you can see that how it looks when the program is transformed by compiler. It looks a bit scary, but also I want to apologize for slides with code, but actually I couldn't avoid it. And what compilers do? It splits the code into sections called extended basic blocks and creates control flow graph or state machine, which represents how the program is executed. Each state can be of two types, sequential and parallel, and parallel states are executed in the vertices as well, while sequential states are executed only in the master. The synchronization between steps are done by using license detection mechanism.
Just so you know, Alex, you have about 5 minutes left.
Okay. Here what we see that each state is represented by an entry function in master or vertex classes. And if we have, for example, for each loop, it is represented in master and in vertex as well. If we have nested for each, we have two separate entry methods in vertex class, and the second one, which is called with the suffix receive, is called from the first one. So it's a call to neighbors. Reduction is done by using standard functions in CHARM++ runtime system for reduction, and using the reduction target methods to receive results of reduction. After the program is completed, callback is sent to return to some boilerplate code. I translated a small set of graph algorithms by this compiler from GreenMark programs and performed some experiments. For SSSP problem, I found actually for all problems except PageRank, I found very surprising thing that translated programs behave a bit more effectively than natively programmed in CHARM++ reference implementation. After investigating why this is happening, I found that when I usually write some graph algorithm in CHARM++, I implement it in as most asynchronous way as possible. But this approach can cause a lot of speculative computation, which is not done in the more synchronous way, which is used in compiler generated code. So that was why it was that was why I saw the difference in the performance. The red one is the red color is the performance of the generated code, and the blue color is the performance of a handwritten code. So that was for the SSSP. Graphs are not very large, and the system is not very large, but it enabled to estimate what the performance difference is. For other benchmarks, for example, connected components, the difference in effectiveness was greater, but when I changed the algorithm to SSC Adapt, it's called, to the one which is used in generated code, so I received similar results, performance results. For PageRank, both reference implementation and generated code had almost the same algorithms, and so the performance difference was very small. So conclusions that a proof of concept implementation of Charm++ backend has been developed, and some performance evaluation has been done, and surprisingly the approach which is used by generator has been more effective than the handwritten naive implementation. In future, I plan to implement more GreenMark specific constructs like built-in breadth first search traverse, and to enable some optimizations in compiler as well in the generated code. For example, to implement Tram aggregations in the generated code. Thank you very much. I'm ready for a question.
All right, I think we have time for maybe one question.
So Alexander, great talk. This is Sanjay. What performance gains do you expect with TRAM? Do you have an idea for how much the fine-grained communication is costing you?
I think it's very significant improvement because fine-grained communication in graph applications are very intensive. So actually, I wouldn't imagine to implement any graph application in Charm++ without TRAM.
Okay, so I guess we can thank our speaker one more time.
Thank you very much.